Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you are doing good. In this, we're going to find building where Alice and Bob can meet. And again, I'm telling we will see the most intuitive approach. And again, I also tell you one more approach. Now, if you don't know, just watch this one reel. You will get a bit of what's happening around the world. Now, coming on back, it simply said that you are given a zero indexed heights array of positive integers where each height represents the height of the ith building. So you have something like this, which ultimately represent some form of heights, as in they are building and this is the height for them. Now, it is also mentioning that if a person is at the building I and they can move to any other building J only and only if the J index is after and also its height is also larger. Which means if I am at an index I and this is index J, J is after and height is also larger, then I can move from I to J. Again, this can also be rephrased as if you are at index any index, again this is any index j, any index I, the next index is larger and the height is larger, then you can move it. So don't be confused by these things, right? Okay, coming on back. Now this other thing that you are also given another array called as queries. Now this is the corresponding queries array which you are given. What this query indicates is that Alice and Bob, for each query, Alice is standing here, Bob is standing here. You have to return that the answer for each query, which is answer of I, is the index of the leftmost building where the Alice and Bob can meet in the ith query. Now, forget about number of queries. Just imagine that you had one query. Again, just imagine that you had one query. If this is the one query, which means I have some form of building like this, Alice is standing here, Bob is standing here. I am asking you what should be on the right side first height which is larger than what they're requiring. So obviously, as you can simply see that Alice is here, Bob is here. Obviously, the height they require, both of them, see, Alice height is 6. So Alice require height more than 6. Bob height is 4. Bob require height more than 4. So they both together will look for height which is more than 6. And considering they both are looking, so they will look after this index. So technically, can't I reframe this specific only this specific, can't I reframe like this, that starting from this index, just on the right side, get me the first height which is larger than 6, which is 8 in this case. So can't I reframe it as that I just want to find, again for each query I want to find the nearest higher height to the right of specific index. And again, index I will get to know which is maximum of Alice and Bob index, and also height I'll get to know which is the maximum of Alice and height, Alice and Bob height. And this is my ultimate maqsad which I want to look for just on the right side. If you don't know, this is a very standard technique called as monotonic stack. If you don't know, just go and watch this one video, you'll get the idea of how to use monotonic stack. Now, when you got to know, okay, it is actually a monotonic stack, let's see what actually is the answer. Again, just a quick, very small dry run of the example statement. As you can see, this is the height. I have shown you the corresponding heights. I will simply erase Alice and Bob. And also, this is the corresponding queries. As you can simply see, query 01, which is the query 0. As I mentioned, that the first height which is larger than both of them is actually 8 at index 2, thus the answer is 2. And similarly, you can say that you can simply try it for the others also. There's just one fact, I mentioned some extra queries. Why I mentioned, you'll get to know just now. But if you look at it, 0 2, the height is 6, this is the height 8. Now, technically, both of them, again, this is Alice, this is Bob. Technically, both of them have to come to one location. Why can't just Alice come to 8? Why can't the Alice come to the location of Bob? Then, again, obviously, I can only jump right side. I can only jump on a higher building, and that is what Alice is doing. So Alice jumped on the right side on the higher building and thus reached Bob. Oh, so for this, the answer will be index 2 itself. And similarly, if I would have mentioned that Alice at index 5 and Bob at index 3, then why can't Bob just simply jump to Alice? Right, he can jump. So what Bob will do, he will simply jump to Alice and thus get the answer. Thus the answer will be 5. And what if both are already at the same index? Oh, then no worries. The answer will be 5 itself. They are already at the same index, so don't do anything. Thus, we simply realize that if I have Alice and Bob, if I have Bob and Alice, if I have Alice and Bob at the same index, so if Alice is here, Bob is maybe after it, and also the height of Alice is less than the height of Bob, then obviously Alice can directly jump to Bob. Same way, Bob can directly jump to Alice. Same way, if both are at the same location, they will already be there. Thus, we can simply get the answer for these kind of queries. What is the query? Queries A comma B, queries B comma A, queries A comma B. Thus, in these queries, my answer will be nothing but maximum of A or B, because ultimately either the Bob jump to Alice or Alice jump to Bob. Thus, again, exact same thing I have shown you here, that in the cases, again, firstly, you will see that this line indicates that I'm always considering my index A, or I should say my Alice, I'm always putting it like this, that okay, so as to compare it easily. Again, you can handle all the if cases, but so that it is easier to maintain Bob and Alice, I am just simply swapping their corresponding values such that Alice is always on the left, which means even if in this case Bob is on the left, I will simply swap their values, which means I will say, okay, Alice and Bob, this is how it is looking like. No matter what, because ultimately I want one person to jump to another. That's it. I am not concerned about who is Alice and who is Bob, right? That's the reason I'm just simply swapping it so as to make the calculation a bit easier. Then in this case, I simply handled that if the height of B, again, you know that B is always on the right side now. So if the height of B is more than the height of A, which means that A can jump to B. So my answer will be B itself, because B, again, I'm mentioning again, B is on the right side. So answer is B. And also I mentioned that even if it is higher, which is this, like these two condition, or even if it is equal, then also, so if my A and B are actually at the same index already, then I should make sure that my answer is still a B. Else in the other case, the answer will be -1. No, Aryan, answer is not -1, answer is something else. As you can see, answer is other values. Oh, no, -1 is just simply a default. Right now, I just put some default value, but I will update it later on. Now, how I will update it? I'll simply have a check just below. If the answer is -1, do make sure that these are the remaining queries which still needs to be answered, because I haven't found the answer for other queries. When I say other queries, I mean the queries like where Alice is here and Bob is here. Now, the next position is not a higher position, so they have to cumulatively jump to a different position. So this is the answer which I have to find. In these scenarios, I will simply say, okay, these are new queries. Simply get me the answer for these queries. Now, you might say how I will get the answer for it. So far you realize that you can simply apply a monotonic stack, but if you remember it very carefully, applying a monotonic stack for just one, it will take O of n time. For Q queries, it will take Q into n time. Q into, if I just show you the constraints, it will take Q is 1e5, 5 into 1e4, n is also 5 into 1e4. So Q into n will give you TLE. Then what to do? Simply just maintain that what you have to find out. What I have to find out? I have to simply, now again, just mention or just make sure the remaining queries. For remaining queries, as I told you before, taking the simple example that for Alice was here, Bob was here. So technically I told you that Alice and Bob together cumulatively are looking for any index on the right side which is higher than the value 6, right? And which query is asking this thing? If you go back, this was the ask of query 0. So I will simply mention that from this index, I have to look for just higher value than 6, and this is the demand of query 0, right? And as you can simply see that this demand can be for multiple queries. So query 0 is this one. I have Alice and Bob here. Thus my demand is higher of both the values, and thus it will be okay. For at this index, which is 1, the demand is that look for a value higher than 6. This is the demand of query 0. Why I'm maintaining everything? You'll get to know just in a bit. But you have to maintain everything just to ask to find the value. Again, same way, this is let's say query 1. At this point, you will say, okay, Alice is here and let's say Bob is here. The value which they're requiring is nothing but 6. So I'm saying, okay, I require a 6. This is a demand of query 1. So I will just simply maintain at this specific index for at the index 3, the demand is looking for a value higher than 6. for the query 1. And same way, at the index 4, the demand for a value of 8 or higher on the right side for the query 2, and value of 5 or higher on the right side for the query 3. Now, when you will simply say, Aryan, how did you make all this? See, if you go back and look very carefully, then I did the same thing. I know that my B is always on the right side of A because of this swap. So I was mentioning the maximum index of both A and B. Again, ultimately, as I have did a swap, thus maximum of both A and B will become automatically a B. This is the max index for both A and B, but I'm also maintaining the corresponding max height of both A and B, max height. And as I told you that when the height of B was larger than A, it automatically became a non minus 1 value. But when the height became same, it became actually, again, when the height became, sorry, when the height of A became larger, then only it actually came inside this condition, which means the max of height A and height B, if it is reaching this point inside this if condition, the max will be always height A, because height B was already handled here when it was maximum. Thus, this is the maximum height of both A and B, and this is the demand of which query this is demanding. As you can simply see, I'm iterating on the queries, so this is the demand of the specific query. Okay, now this is the ultimate aim, ultimate maksad. Now let's start it. Let's start what we should do and what we are trying to do here. So if you look back very carefully, we told we will simply try to use a monotonic stack, and obviously the hint itself, again the biggest hint itself, this problem gave us. Again, many people used segment trees, many people use priority queue. I'm not mentioning about that. I'm mentioning about the biggest intuition at this point, because in an interview, coming up to approach itself is a very big task. Now, out of nowhere, I can think of priority queue, right? That's the thing. Cool. Coming on back, we realize that now ultimately we have to find the answer. Let's do it. So we realized we'll use a simple monitoring stack, and we realize that at every point or at every hub, I have the value, okay, which means after this index, I want to know the answer for these two queries, and this is a demand. Okay, I should look for higher than 8, I should look for higher than 5, but always look for the right side. So as I also told in the previous video, this one, that we always iterate from the right side in these cases, because I have to look for the right. So what I will do, I will simply come back and I will start iterating from the right side. How I will iterate? I will simply say, okay, bro, simply iterate it, which means that do you have to look for anything for this index? Is there any queries you have for it? No, I don't have it. Simply push that to your stack. I pushed it. Now you might say, Aryan, okay, if you simply pushed it into your stack, you mentioned that it is monotonic, and in the last video also you told us that how to, again, figuring out monotonic is one thing, but figuring out if it is monotonic increasing or decreasing is actually another challenging task. So how I will do it? Okay, let's see. So I simply realize, okay, I'm moving the screen a lot. Do make sure that it's not intentional. It's actually, I wanted to show you everything. So I now have to figure out, will it be monotonic increasing or decreasing? Again, I know it's monotonic stack, but if it is increasing or decreasing, that's a question. Simply in these cases, just look at the example at a random location, which means at an index I, if I am at this value 4, right, and I know I'm moving on from the right to left, so will I look for a higher value or a lower value? Obviously, I will look for a higher value, just higher value on the right side, which means that even if I would have a value of 5, this will be overridden by a value of 8, which means that 5 as a smaller value in beneath the stack is not useful, which ultimately means that the stack will be such that the smaller values are at the top, higher values are at the bottom. Because obviously you can simply see that if I would have had a 5 here, then when 8 would have come in, because for 4 or for any other value maybe on the left side, 5 is of no use. 8 is actually the actual one, which is much better or much useful. So we realize that any smaller value is being removed from the stack, which means the smaller value is removed from the stack from the very bottom, which means it will be remaining at the top. So the stack will be monotonically decreasing, which means, okay, it is 7, then I will have a lesser value, lesser value, lesser value, lesser value. This is how I will maintain my corresponding stack. Now, if you want to see the corresponding code, you will simply have a simple value. If you see any value which is lesser on the top of the stack, which is lesser, Now you might say, Aryan, what is this back? Technically, you use a push pop or top, right, for a stack. I'll say yes, but I'll come on to it a bit later on. But again, just for a quick glimpse, if you don't know, a stack is nothing but simply a vector or simply an array. So I can also maintain a vector in which I can simply push things from the top, remove things from the top, or I should say the front. That is also a stack, right? So this is how I have used it. Now you might ask why. I'll come on to it later on. Now, so you realize, okay, if it is actually less value or equal value, simply remove it from the stack. Okay, now I know that it is how I will maintain a monotonic stack. But on the other hand, same thing that, okay, this is the value when you were at index 5, you just pushed it because there was nothing query as such. Now you jumped on to the next index because you are moving from right to left. So you are at index 4. At index 4, again, you are looking for these two queries answer, which means that you are looking for, and you will simply say that, okay, for query 2, I'm looking for any values higher than 8. Now, technically, you might say, Aryan, okay, I'm looking for higher than 8. So, firstly, how should I approach this statement? Because here, for one index, again, that's a very, very, very important point. I'm stressing it very, very, very much. So, make sure this is very important. For one index, which is 4, I have two demands of two different queries, right? And these can be many more demands. For each demand, I have to look for inside the stack what is the best possible value. Now, why I'm stressing on this is because what if your stack would have looked like 9 comma something, 8 comma something, 7 comma something, 6 comma something, 5 comma something, 4 comma something, 3 comma something. Now you might ask that, Aryan, it feels like that for value 5, I have to look for any value which is higher than 5 but also in the stack. So technically I will remove all the values which are lesser, right? You might do it, like you might have a gut for it. Okay, I'll tell you why it is not, why it's very bad. But you might remove all these values which is lesser than or equal to 5. Now you might say, Aryan, but I encountered 8 earlier. So what if I had removed all the values up till here? Then I would have encountered 9. Technically, yes. So then you might come to a conclusion that considering I am having value 8, I am having value 5. So I will simply sort these. Again, this is what you are thinking in your mind right now. That I will simply sort this. And by sorting this, what I will do that, okay, I will simply encounter 5 earlier. So I will firstly remove all these values. Then I will get the 6, which is the top of the stack. I will simply put it here. And then again I will simply get the answer for 5, which is removing all these values. I'll get the answer for 8. But okay, so far you did good. But if you remember, the things which you're pushing in the stack, again, this is one such fact that things which you're pushing in the stack is actually the actual heights. These are the actual heights which are pushing in the stack. So it is not linked with the query. But you might say, Aryan, this is also the query demand, right? Query demand of height itself. So why can't I link it? Okay, if let's say you linked it, what about this query? It is on the left side. What about this query? You technically removed everything up till index 8, but you are now asking for a height of 6, which may not be on your stack. Oh, that's another issue. So far, one thing we realize is that we cannot just, for these queries, we just simply cannot remove. Okay, where it is gone? Uh, 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 okay. Yeah, for these queries, we can just simply cannot remove from the stack everything. No, we cannot. Okay, we realized one thing that we have to do a search, but that technically feels like a simple search on the entire stack. Again, that is costly, I know, but this is the ultimate thing that you will have to search. Again, I will come on to this point of searching also, but a bit thing. Okay, I will have to search in the entire stack. If that's the case, then what to do? Okay, in this situation, I guess I have to search the entire stack. Currently, in this case, I only had one thing, which is 7 comma 5. For this query of 8, there is, again, after doing a search, which is a linear search, I did not find anything which is higher than 8. So answer is -1. For 5, okay, I realized it is the first value, which is index I5. So the query 3, for a value of 5, high value is 7, Index is I5. Index is I5. Again, I have showed you I5 Q3 because I don't want to confuse it by query index and the actual index itself. Now, you might have a very basic doubt because as you move forward, you will simply push this value in the stack. As I told you previously also that this is a monotonic decreasing stack, which means that you will push a lesser value. If it would have been a higher value, you would have removed the things from the stack. But as you did a push, you realize that you are doing a linear search and you are finding again the same thing, that as you move backwards, you will simply do a linear search. You're trying to find some things in the stack. If I emphasize this thing again, I told you though that if you even look at this specific example where for the query 3, you have a maqsad to look for a value 6 for a query 1. In this scenario, what you are trying or what you are doing here is that you will simply iterate, and if after iterating, if for this query you would have removed this thing, again I'm not saying for the input, which means heights, for the query if you would have removed this height from your stack, then what could have happened is, what if in the previous index, what if my demand would have been for the height of 1? In that case you would have lost this value, and that's a simple fact that you could have lost a specific value which you could have used it. Thus, again, if you just want to see one more example, just look at this specific example, that like for the specific query, ultimately imagining that I am requiring a value of 5, here I'm requiring value of 6. So if I would have removed everything which is higher than or equal to 6, then for this specific value or for this specific height, I would have not find anything in my stack. So for queries itself, I cannot remove anything from the stack. When I'm iterating on the height, then I will remove things from my stack. Okay, which means that I'm doing again a linear search, but so as to do a linear search, I'm just simply trying to iterate on this stack. But considering again, very simple, very basic observation that the stack is monotonic decreasing, thus I will or can simply use a binary search rather than a linear search, and thus making my complexity go higher. And because I'm doing a binary search, that is the reason I took a vector rather than a stack, because I cannot do a binary search on stack, but I can do a binary search on my vector. That is the reason I took a vector. And again, vector represents the same thing as stack, because in a vector you can push from the front, you can pop from the front. This indicates a slanted stack. Cool. And that's the reason we'll use a binary search. Again, the very important fact was that how you know the queries will not modify your stack and only the index will modify your stack. If you don't understand it, just go and watch the last 5 minutes again, because that's a most important point. Coming on back, let's complete the dry run. So ultimately we realized that I was at index this one, which means in index 3. My maqsad, my demand was a value of 6. I simply did a binary search. I could not find anything. Or yeah, I could find. After doing a binary search, I landed on, and it landed me to the value of I5. Okay, I5, its value is I5. Then I will push this current value in the stack, which means I'll push 5 comma I3. But as I told you, it is a monotonic decreasing. So this will be removed from the stack because of this push. Then I will go on to the next index, which is I, like this one, this index I. Again, he has no demand, so simply push it in the stack. If I push it in the stack, anything which is lesser will be removed, so I'll simply push I2. Okay, now move on back. This is the corresponding index. I will simply check. Okay, his demand is looking for a 6 for query 0. Okay, I'll simply do a binary search. I will land onto here. He will give me I2. I'll get him the I2, and then I will push him in the stack, which means I will push 4 comma I1 and then move backwards. Okay, he has no demands. If he has no demands, simply push it here, and then which means I'll push it by saying that 6 comma I0, and then that is it. I'll simply reach my end, and that is my corresponding answer for all the queries. Again, I will quickly, very quickly, before showing you the corresponding, okay, let me show you the code first. So for the code, again, we simply took a stack. As I told you, it is a vector rather than a simple stack, and in my vector I'm maintaining the pair. One thing is the height, another thing is corresponding index for it, index for it, right? Then I also have the corresponding answer, which will store the answer for all the queries. Then I have a new queries, as I mentioned that when I was iterating again, this is the exact code I showed you in the dry run also. In this specific, I told you that I will just put up all the queries which are unresolved. Then I will go on to all of these queries, but from the right side. I told you why from the right side, because when I was telling the monotonic stack approach, then I will go on to all the queries for that index. Again, don't assume that Aryan, this is q into q. No, this is going on to all the index. Sorry, it is n into q. No, it is not, because ultimately what is happening here is that you're iterating on this index, which means that you are iterating on all, oh sorry, yeah, all the indexes from the right side. For every index, if it has some queries listed in its index, you're going into them, which means at max n indexes, and ultimately cumulatively as a sum I could have q queries. As you can see, 1 2 3 4, 4 queries at max. Again, it can become at max q queries because I have removed from here all the queries which were actually from them to themselves, which means all these queries are removed. So even in worst case, this new queries can have at max q queries. Thus, this complexity will be q plus n and not q into n. Now, coming on that, I will simply do a binary search for the position. If the position is -1, the answer will be simply nothing. Again, if the position is not a -1, the answer will be the position which I got. If it is -1, obviously by default I have already placed a -1, so there's no change I should do. But also making sure that now I have to move to the next index, which is the previous index. So I will make sure to empty the stack as much as I can, which means making it monotonic decreasing and also pushing myself. That's important. And ultimately keep on repeating this process, ultimately getting the answer. With this, as you can simply see, your complexity will be q log n, because for every query technically you're doing a binary search, and the binary search input field can be at max n indexes considering all are present here. And obviously the space will be n plus q because you are using many extra things here and building many extra stuff. Now, before wrapping up, I just want to tell you the one more again simple approach. It can be solved by segment trees, priority queue, anything whatsoever. Again, the idea remains still same, that for any index you are looking for things which can actually solve its havas, which means its actual requirement. So if my requirement is value of like a value like a height of 6 or higher on the right side for the query 3, I can simply assume the same thing as that. Okay, for this specific thing, which means the specific index, I can simply, again, there are multiple ways to solve it. Again, I'm again telling multiple ways to solve it, but I can maintain the actual height and which query I want, which means that maintain the highest height which you can have, and also for which query this can satisfy it. Which means if I'm using, again, this is simply by using a priority queue, I have to maintain a highest height as I am moving on from left to right, maintain the highest height which can satisfy the greed or the requirement of any query whose demand is xyz. Which means in this specific case, when I have 8 and 5, so I'll just simply look for, can I get the corresponding highest height or not. And that is the reason I told you range max, right? Simply maintaining the maximum value, all that stuff is the primary reason why we can use a priority queue or a segment tree. Again, if you want to refer the code, you can find here itself, but I'll not explain it because again the video is already long, and this is also something which I feel like was not that intuitive. And as intuitive, you will feel like that the moment you know that you have to apply a priority queue and the person will explain it, it will look easy. But easiness will be when you start with that approach. What if you never even came to that approach? That is the reason intuition is the first primary thing which should be the factor to make you feel that was this problem a easy approach or not. Bye bye, take care. Make sure if you liked it, please smash the like baby. Bye.